Hiya and Wanju. Hello and welcome to today's New Waterways webinar. It's about future climate, future home, adaptive urban design strategies for WA. Very exciting. Firstly, I would like to acknowledge that I am on Whadjuk Noongar Budja and pay my deepest respects to the continuing culture of the Aboriginal people here and also across the countries where everybody is. So we have mostly people from WA today, but there are some interstate people as well. So welcome everybody, and just feel free if you would like to chuck in the chat, acknowledge the country that you are on today. That connection to country is so important for us to be able to manage what's going to happen into the future, as Jules is going to talk to us about. My name is Shelley Shepherd. I am the Program Manager of New Waterways, and New Waterways is the West Australian Capacity Building Program for Water Sensitive Urban Design. We have a fabulous group of program partners who are the Department of Biodiversity Conservation and Attraction, the Department of Planning, Lands and Heritage, the Department of Water and Environmental Regulation, the Urban Development Institute of Australia, WA, the West Australian Local Government Association and the Water Corporation. So thank you to our program partners for sustaining this program and keeping it going for the last, over 10 years now. So I'm very excited today that we will hear from Associate Professor Boliter regarding the outcome of this amazing research. Isn't it going to be amazing to understand what the outcome is of our planning, building paradigm, knowing what's coming in the future? So this is going to be really awesome. But first of all, I just want to remind everybody that we will have time for questions afterwards. So there are the Q&A and the chat function. So if you can chat to people in the chat function, say hi to some people, check out who's on. We've got nearly 60 people at the moment, which is really exciting. So please say hi to friends. This is about building a community of practice. But also if you do have a question, pop it into the Q&A function and we can talk to that after Jules's presentation. Thank you, Emily, Kaya as well. So the other thing that we are trying to do, but I don't think you're going to see it here, it might just be in the video, is we're enabling the captions. So I'm not quite sure how they'll turn out, particularly from my perspective. So therefore, there will be a recording of this, which will be available on the New Waterways website, probably in a week or so after we get all the permissions. So thank you again for everybody coming along today. I'm very excited to introduce Associate Professor Julian Boliter, who is the Director of the Australian Urban Design Research Centre, also known as AUDRIC, at the University of WA. He's the Program Director of AUDRIC's Master of Urban Design course and an author and a public figure, as most of us know. Jules leads the ambitious climate adaptation project, Future Climate, Future Home, Adaptive Urban Design Strategies for WA with AUDRIC partner organisations, and I'd like to acknowledge Development WA, the Department of Communities, which are now, I think, is called the Department of Housing and Works, the West Australian Planning Commission, and multiple local governments. So now I would like to hand over to Jules and welcome everybody to today's webinar. Thank you.
Hi there, Dr. Julian Boliter here from the Australian Urban Design Research Centre. Today I'll be presenting on our project Future Climate, Future Home, Evidence-Based Adaptive Urban Design Strategies for WA. The project is supported by multiple state and local government partners. The overarching objective of the project is to generate evidence to inform solutions and policy decisions concerning the climate change adaptation of urban precincts and housings to projected temperature and rainfall changes across WA's diverse climate regions. The presentation I'll give is in 4 parts. We'll be looking at the urban precinct case study performance of different precincts from Broome in the north to 2J in the east and down to Perth. We'll be looking at how they perform in terms of current climate and thermal comfort in their current climate. We'll be looking at how that might change under different scenarios and timeframes in terms of future climate projections. And we'll be looking at how we adapt urban areas to future climate change and in particular increasing temperatures, and we'll consider some next steps. So firstly, to current climate performance. The objective of this phase is really just about benchmarking the performance of selected urban precinct case studies concerning outdoor thermal comfort in the current climate. So ignoring for a moment climate change, in Australia, heat waves midsummer in summer trigger what are considered more than 1,000 extra deaths annually. So reflecting this in the terrible Black Saturday bushfires, we know that twice as many people were killed by the crippling heat than the fire. And the reason for much of this is because extreme heat conditions significantly disturb people's thermoregulation, which can have severe consequences for vulnerable groups such as children, adults, obese people, and people suffering from heart, lung, or blood pressure conditions. So there's been a lot of focus, I think, on, and rightly so, on these extra annual deaths and the mortality that can go with heatwave events. But it's also, I think, interesting to focus for a moment on the effects on a society that occur even with marginal increases in temperature. So we're not necessarily talking heatwave events here. So this sort of flowchart here, it's really based on this book called Slow Burn by Jisung Park, The Hidden Costs of a Warming World, which is really good at unpicking the kind of consequences of even quite modest increases in temperature across the economy and across society more generally. So with increased heat, as we're experiencing, typically in terms of the economy, we find lower economic productivity and more mistakes being made, certainly in unair-conditioned kind of workplaces, increased workplace accidents, and a reduced rate of student learning in schools. So this is data that's coming out of the US, where a number of schools, particularly in lower socioeconomic areas, are not air-conditioned. And the degree that the kind of degree of increase in temperature in any particular year can be discerned in correlations with national scale testing of students. So there's definitely a kind of a hit to productivity which goes with this gradually increasing climate. In terms of health, with increased heat, we find reduced physical exercise as there's a retreat to interior environments and cars, which of course has a flow-on effect in terms of people's cardiovascular health and others. We have a worsening of underlying medical conditions with increased heat, increased mental health disorders, increased suicides, and reduced sleep, all playing out across the domain of health. In terms of society, we have typically reduced community interaction as people are retreating to air-conditioned environments. We even have increased violent crime, murders, assaults, and bullying in schools, and even increased online profanity. So as the temperature increases even to a small degree, we start to have these kind of effects playing out at a population scale, a population level across a society. The combined effect of all of those is societal and economic harms, lower GDP, and a kind of a gradual sort of reducing of capacity of society as this societal and economic harm is brought to bear on it in terms of its capacity then to adapt to climate change. And so therefore then further increased heat can then be exacerbating those same conditions, which then make it even more difficult and reduces the capacity of society to really deal with climate change and this warming. So there's an insidious kind of vicious circle occurring here we can see. So with that in mind, what we really did in this first phase was to take these 12 case studies, which are all different urban precinct case studies, and to model them in sophisticated microclimatic modelling software called NWW. So we won't go into all of these because we don't have that much time, but just to give you a brief introduction, we looked at Broome North, which is a climate-sensitive urban design development delivered by Development WA in Broome, traditional urbanism in Broome, which is quite well climate adapted, Karratha and a suburb of Karratha called Bulgara, a large park in Geraldton called Maitland Park surrounded by schools, a new suburb in 2J, and then down to Perth, really looking at a classic kind of compact suburbia in Kimberley, a classic background infill run ride in Nollamara, Leederville Town Centre, which is a TOD, Coburn Central, which is a TOD, and Salt Lane, which is a new Development WA project. So these were our case studies, picking up different socioeconomic vulnerabilities in different urban forms and different climate conditions. So let's start with Jindalee. So we know this is a kind of expression of livable neighbourhoods policy, which is about compact suburbia. So we typically have quite small lots dominated by houses, which in many cases are quite large, a rectilinear kind of grid network, and a kind of a focus on local parks where we prioritise the accessibility of parks to houses, but generally they're not particularly big. So this is really the work that goes in terms of NWMET, in terms of digitising one of these 500 by 500 metre precincts. We can see there in the top left, we digitise every surface, every paving material. We digitise every tree, and the trees are digitised in terms of species. So we created these trees in NWMET to reflect accurately the kind of species you might find in a precinct. So things like the leaf area density is modelled, the size of the crown, of course, but also the potential and the ability of that tree to evapotranspire water for cooling effects from the stomata and its leaves. So there's a lot of detail that goes into these models. They again fed into a kind of supercomputer, which then takes a week to run, and we get all this kind of really fascinating climate outputs shown in these maps here. So I'll just run you through these. And really, I think this is an expression of how difficult it is to understand what's going on in terms of urban climate when you have so many different variables and indices for measuring how we might be experiencing thermal comfort. So in the top left, we see temperature of surfaces. So that's often referred to as land surface temperature. And we can see there, as we would expect, the roads, which are dark and have a high thermal mass, are absorbing a lot of heat, and they're much hotter than the parks would be, for instance. In the middle top, we have air temperature. And the top right, we have radiant temperature. So this is shortwave radiation directly from the sun, but also long-wave radiation that might be bouncing off walls and paving and fences. And we can see, really significant radiant heat there around many of the building forms. Wind in the bottom left, so the sea breeze has just come in. So this is a simulation of an average summer's day, and we can see those north-south running streets are funneling wind effectively. Humidity in the middle bottom, and finally, most importantly, is the physiologically equivalent temperature, which is in the bottom right. So PET, as it is known, is a thermal comfort indice which takes into account humidity, ventilation and wind, radiant temperature, air temperature, and then factors in also the kind of clothes the person might be wearing and the degree of recreation they're doing. And then it gives us an estimation of the thermal comfort they would be perceiving in that environment. And here we can, just zooming in a little bit into the PET, physiologically equivalent temperature map for Kimberley. So what we can see here is there's a significant amount of heat stress going on. So anything over about 35 degrees is considered strong heat stress, and over about 42 degrees is extreme heat stress. PET is higher than air temperature, should be noted. But it's really interesting to look at this and realise a lot of where we're experiencing compounded thermal discomfort is around the houses. So it's in those areas which are not well ventilated, as we saw in that earlier map, where we're having radiant heat bouncing around off hard surfaces, where there are no trees or very little trees to provide cooling. So you're essentially getting this kind of heating effect exactly where you really don't want it, which is around the houses, where people in the middle of summer are most likely to try and get outside. And it's also where those conditions will be compounding the energy use required for cooling. It's interesting to note the streets, particularly on the west side, are funneling a lot of that sea breeze through and are actually very cool. So I think this cautions us from looking at a climate performance purely in terms of what's going on with sun and shade, which is typically major drivers in thinking about climate-sensitive urban design. Wind is, according to this metric, really important, and we can see those areas where ventilation is lacking as causing problems. So let's have a look now at Nollamara. So this is background infill where we've got 3 packs, 4 packs, 2 packs being built in people's backyards. And we can see the NVMet modelling of that densified urban form here in all its detail. So again, looking at similar outputs for Nollamara, we have the surface temperature in the top left, air temperature, mean radiant temperature, again, very high around the houses. Ventilation in the bottom left. This is, I think there's might be a bit more west in this breeze, and we're getting some wind funneling down those east-west running streets. But looking at the PET, which is the main game in terms of how people experience thermal discomfort, again, a significant amount of a summer's day, an average summer's day, people in this environment in the sun would be in a state of strong heat stress, 54% of daylight hours, and extreme heat stress, 46%. So what's to notice here? Again, that same issue around the housing. Seeing those compounded kind of little heat islands forming there where we have, a semi-detached or attached housing being built without attentiveness to ventilation, where we have full-height fences, where we have very few trees. And interesting to note, under the trees, you can see on some of the streets these cool spots where there is shade from particular trees. But interesting to note in the sort of top left here, there's some real cool areas opening up under some of these trees. And of course, so they're trees that typically have a high leaf area density, so it's a solid shade. Often more exotic trees are still evapotranspiring water and giving a cooling effect by virtue of that evaporation. So a tree is not a tree, and it's very much, some trees are much better adapted to providing cooling. Interesting to note a small park here without irrigated grass, as has been modelled, and without significant tree canopy coverage, not producing a lot of cooling. Of course, that's not a fault of the park, it's more a factor of the lack of tree canopy coverage in that park. Okay, so when we look across all the case studies, we find that certainly the extent of strong and extreme heat stress is most high in those northern case studies, being Broome North, Karratha Town Centre and Bulgara. Although it's interesting to note, Broome Central, which has a very good urban forest, spacious urban forms and is typically well ventilated, certainly performing better than its northern counterparts. So, I think the estimations and ranking of the case studies in terms of strong and extreme heat stress is a factor of the broader macroclimate, but it can be mediated to a degree, as we can see in Broome. Of interest to people today would be that we've also looked at some key drainage land case studies here, which were ventured by Water Corporation, who are one of our funding partners for the project. So the Wharf Street Basin in Cannington on the left there, which many of you would know well. Peters Place in Morley, which is an open drain, also with a compensation basin and a local and neighbourhood open space appended to it. And Dunnell Street Park, again on an open drain in Maddington, with a local neighbourhood open space. So today I'll just present Wharf Street Cannington, which is a significant body of water which has been upgraded with boardwalks and macrophytes and tree planting, and is in a quite, is within a hard edge kind of urban context, and so interesting to see the kind of cooling that yields. So not surprisingly, as we can see in surface temperature modelling here, in the top left, the roads are very hot, the asphalt's very hot. Of course, the water here is quite cool in terms of surface temperature, and we can see that it's also generating a significant cooling effect. Depending on where you draw your comparison to, potentially up to 5 degrees in the middle top here, as that water is evaporated off the surface of the water body, we can see there's a cooling effect of air. And then, so looking down in the bottom left, wind, so there's plenty of ventilation over it, and we can see the humidity increasing significantly in that water, above that water body as that water is evaporated. And we can see a significant decrease in physiologically equivalent temperature over that body of water and immediately adjacent areas. But it doesn't extend particularly far. And I think that's where we find there's a kind of limitation here in terms of the degree to which a water body, at least in the conditions we've modelled, is cooling the area around it. And certainly we find still the coolest places within that quadrant, in that case study, are under trees. And we can see that in the bottom right, trees with a high leaf area density ratio are producing significant cooling. But nonetheless, there is a significant cooling of air temperature going on. It's just not necessarily registering in terms of physiologically equivalent temperature at a significant distance. So we'll be confirming this with real-world measuring in the coming summer and looking forward to running some transects through this environment. Sorry about that little pause. Okay. So, of course, modelling is all well and good, but modelling is only ever a kind of crude approximation, or hopefully not too crude in this case, but it is an approximation of reality, which is inevitably more complicated. So one thing we've been doing over the last summer is working with Audric staff member James Lund with a device that we've established called Brolytron 2000, which is a trolley with an umbrella and a number of different thermometers measuring land surface temperature, air temperature and humidity, and really walking across transects cutting across various parks in Perth to understand the degree to which they are delivering what is called the cool island effect. The cool island effect is, there's a lot of literature on this, is the degree to which parks provide a cooling refuge and also potentially cool the areas around them. Generally, they're measured in terms of air temperature and land surface temperature. So these are the metrics we have focused on. We were particularly curious about parks like Garrymeink Park in Butler here that you can see, which is a livable neighbourhoods park in a compact suburbia, which is responding to the fact that there is we're experiencing declining rainfall in Perth and there's less water for irrigation, so much of the park is xerophytic. But we were really curious as to the degree to which a park like this might be producing a cooling effect. So we can see Garrymeink Park here. We can see the transect we've walked from the start in the north there to finishing in the south. And essentially, the points along that are measured here, are represented here in the graphs. And we can see Garrymeink Park walking from north to south on a typical summer's day. Both we did 7 to 8 a.m. in the morning, 2 to 3 in the arvo, and 8 to 9 at night. We really found that there was very little cooling effect in the park in terms of air temperature. In terms of surface temperature, however, we can see a much more significant drop-off in temperature here. What is that, almost 20 degrees, depending on what point you make your reference during the middle of the day. So obviously land surface temperatures are dropping off considerably in the day, but also in the morning and the evening, and relative humidity going up at between 2 and 3 in the afternoon as we walk the transect. And we realised later that's because the sea breeze had come in and actually the level of humidity had gone up. This is land surface temperature data sets produced from the Landsat satellite, which we've just used here as another point of reference. But really what that's showing is it's more about the coarseness of this data set. It's not really picking up the park at all. So the question would be, why is it not producing a major cooling effect in terms of air temperature? The reality is, with a small park like this, that any decrease in air temperature would be quickly dispersed, as you can imagine, particularly as the sea breeze comes in. But there is also not much in the way of shade in the park. And while the park is irrigated, it might not be producing much of a cooling effect that's registering at the height of our sensors, which are, approximately 1.2, 1.3 metres high. So this was a less than significant park cool island effect. We also looked at McNaughton Park, which is in, where is McNaughton Park? Kinross, thank you. And again, walking this transect from the north here at point 1 down to the finish, taking measurements about every 25 metres. And certainly we found about a 1 degree perhaps cooling effect in terms of air temperature as you move through that park. The yellow boxes here are denoting this area of park. The second box denotes this area of bushland here, which is interesting. So during the middle of the day, there is some cooling effect. In the morning, it's interesting that the park is actually a little bit warmer, and perhaps it had been irrigated and that moisture has been able to retain the heat longer through the night. Surface temperature, we find a big drop-off, almost 20 degrees in land surface temperature during the day as you move through that irrigated oval. But then it's peaking again as you go through the bushland, which is not irrigated, which is interesting. In terms of relative humidity, again, that's certainly increasing over the oval during the middle of the day and in the evening, but less so over the bushland. So again, it's there's 1 degree air temperature difference, obviously much more significant in terms of surface temperature. But we'll get to these kind of subtleties of those two measurements in a moment. A High Park, we thought, would surely, of all parks in Perth, given it sits within this hollow which would cradle cooler air, it has huge canopy cover, and it's a significant size park, and obviously the evaporative cooling of the water body would be expected, I think, of all parks in Perth to produce a really measurable decrease in air temperature. And certainly we found that during the middle of the day, walking that transect from the north to the south through the park, there was a sort of 1 to 2 degree potentially kind of temperature decrease as you move past those water bodies. So definitely a measurable cooling effect there that's going on. Less so in the evening and in the morning, curiously. So again, whether that cool air is being dispersed by that point, I think is probably what's going on. Again, surface temperature decreases as you move through the park is significant. And it also registers on that Landsat aerial remote sensed land surface temperature data, which we can see here. So significant cooling going on in terms of land surface temperature and the humidity going up, as you'd expect. around the water bodies. So in summary, across those three parks, the park cool island effect is definitely at work here, particularly in Hyde Park, and we can see that in that 1 to 2 degree temperature decrease, which is not insignificant. But it is a little underwhelming perhaps in relation to some of the research which focuses on land surface temperature as a marker of park cool island effects. And we see this in a number of published papers where park cool island effects, by virtue of land surface temperature, could be 10 to 20 degrees different. So when we're talking about air temperature, it's much more subtle than that. And so the question would be, well, why wouldn't you focus on land surface temperature? And I think it's really important to clear up this misconception that land surface temperature is generally not thermal comfort directly, right? So take, for an example, a Hillcrest Reserve in Bayswater, such as we can see here, registering on the land surface temperature generated remote sense data set here in the bottom right, is showing it's significantly cooler than the area around it. What is it, 5, 10 degrees cooler? That's fine, but that is not how we typically would experience thermal comfort. So a cricket player standing out there in the full sun, even though that grass is much cooler than it might be of asphalt, their dominant experience of thermal discomfort is going to be from the sun, which is hitting them effectively directly. So we need to be a little bit careful about directly correlating land surface temperature with thermal comfort. Of course, the two do relate in certain ways, but as this example provides hopefully an insight, the two are also quite different. So this is a figure reproduced by other researchers, but essentially it is showing in Phoenix, I think it is, temperatures, both air temperatures, which are the bottom lines here of grass, of desert and asphalt, and then the dashed lines, the equivalent land surface temperature recordings. So what we're finding is even when the land surface temperature of the desert is really peaking, like this in the middle of the day, actually the air temperature just above it isn't really changing very much. So land surface temperature can differ quite substantially from air temperature. Of course, the two are related, but they're not the same. So we need to just be a little bit careful about research which uses land surface temperature alone as an estimation of thermal comfort. So what is all this telling us? I think what it is telling us of the cooling effects of vegetation, the most important in a sunny place like Perth is going to be shade. So therefore, it's about tree canopy cover. So as Brown et al. Tell us in their paper, that in very hot and sunny climate zones like Perth, parks would ideally look like forests. So when we take a park like Garrymeyank Park up in Butler, and we don't find a significant park cooling effect, and presumably it's not providing very good thermal comfort, it's not so much a fault of the park, it's a fault of the fact that there's unlikely to be enough tree canopy cover in that park to generate that cooling effect and to provide the shade, which is the most dominant and important thing in terms of climate adaptation to extreme heat. So what does this mean? Does it mean parks are not important because it's only 1 to 2 degrees difference in temperature, say in Hyde Park? Should we just get rid of it? Absolutely not. That is not what we're saying, and parks provide a multitude of ecosystem services. But what we were saying is it's about interconnected networks of shade and tree canopy cover is the most important thing. Thermal comfort in Perth is most defined by exposure to the sun, and therefore shade is most important. So we need to be thinking about not just singular parks and park cool island effects, but we need to be thinking about interconnected shade networks, connecting schools, connecting public transport hubs, connecting parks into one continuous matrix of shady networks. And obviously parks are one of the least contested places where we can plant big trees. Difficult in backyards, difficult in streets often. So parks are really where we should be going for it, and they hold such opportunities. But we shouldn't see them in isolation from providing shade and cooling in the rest of the urban environment. So look, in the second part of the project, we'll be looking at the same case studies in the context of alarming projections from the IPCC and others, and we'll be analysing those same precinct case studies to see how their climate performance will change over time. And here we can see just Kimberley again, and here we've rerun the PET map, the physiologically equivalent temperature map, with the same colour scale, and you can see the shift there. And what we're showing here in this bottom PET export is really the areas which will experience the greatest absolute difference in PET, and we can see that's getting up around 7.5 degrees. In some of those areas we were talking about earlier where we have that exposure to the sun, where we have a lack of ventilation. So we'll be testing all the case studies in terms of their future climate performance. This work's ongoing and that report's still to be issued. Of course, what do you do? So we've been scouring the resources and digging up a whole myriad of different urban adaptation strategies for extreme heat and testing them through a number of surveys which look at how you might adapt streets, how you might adapt parks, and the streets being either suburban or urban, and how you might adapt suburban form and urban form in the form of low to mid-rise apartments. So these surveys are out there at the moment, and be grateful if you would consider taking them. They ask experts like yourself to rate different climate adaptation strategies for both their likely effectiveness and feasibility. We will take the results of this and then we will actually apply them in our modelling, in our case studies, to adapt them to future climate. Our next step, we disseminating the survey, and be grateful for your input on that. We will be issuing the Phase 2 report, which is about the future climate performance of our case studies in the third quarter of this year, and then the climate performance of the adapted case studies towards the end of the year. And over this summer, we'll be doing more park measurement. Particularly, I would love to do some more measurement around the Wharf Street Basin Park, amongst other parks, to continue to explore the existence of the park cooler-land effect. So really, thank you for listening. Exports of reports and things are available on our website. Appreciate the opportunity to present to you all today and look forward to a discussion. Thank you.